Good. So let's see. Can you see the slides? Yeah. Somebody can say whether the slides can be seen?
I can see your slides.
Good. Thanks. Yeah. So thanks, Depo, for introduction and for putting this together in these weird times. So yes, Depo was saying I'm going to talk about Mu, which is well, we always describe as kind of a purely functional framework to build in microservices. And well, the idea here is that we really want to do something in which we can use all the functionality that Haskell provide us in order to build these microservices. So we go from very high level from using type level information to encode schemas and service definitions. And I'll talk about it a bit later. And we go into the low level and try to also support a wide range of serialization formats. So gRPC, GraphQL, and all of that. And if you look about Mu, which is a kind of a short name, but if you look at Mu, what we are doing in 47 degrees, that's the company where I work, you will see that we actually are developing both Mu for Haskell and Mu for Scala. So we try to keep those two things par on par. So as you could imagine, the company works a lot with microservices. So it's also in our own interest to develop these tools. And what we try to do is try to figure out what we want. So we want support for these formats, but then we want to evolve the two things into their idiomatic solutions. So you will see that if you compare Mu-Haskell and Mu-Scala, they have the same goals, but they evolve completely separately, and the kind of techniques we use are different depending on the language. But after this introduction, let me first say a word about the version. So if you look at the website of Mu-Haskell, you'll see that the stable version is 0.2, but actually I'm going to talk about the upcoming 0.3 release, which should be released in 10 or 15 days. And I want to talk about it because we actually simplified the API in a bunch of different ways. And I also can talk about something we've been working on for the last 3 months, and I'm kind of excited about, which is support for GraphQL. So again, if you don't know what GraphQL is, I'll explain about it later. But let me start with how you use Mu for gRPC. And in case you don't know what gRPC is a format to to do RPC calls, and the G comes from Google because Google is the company which is backing this app. And the whole idea is that instead of using, like your Java RPC or your Python RPC or your actors or whatever format you want, what they try to define is a format which different languages can use. So what you do actually is to define how your gRPC service looks like in a file, as I'm showing on the screen. So you define the shape of your messages. So in this case, we have like a hello request, which is a string, and a hello reply, which is a string. And you define that your service has a method say hello, which takes a hello request and returns a hello reply. And it all looks very Java-like, but actually the format is quite simple. Everything you have can only take one argument and can only return one thing as a result. And then, well, there is a format about how you should transmit and do this RPC. But actually, the gRPC is agnostic on the way you serialize your message. But in practice, most people use protocol buffers, which is yet another format defined by Google engineers to do this. So sort of most people use just gRPC with protocol buffers, although in the library we also support gRPC with Avro, which is the serialization format used by Kafka, among other things. So this is something that you usually get or you share in the company. So in the kind of scenarios we see when we do some work at 47, well, just a company just defines a bunch of these services, and these are all the microservices that are are used within the place within the system we're working on, and this is what allows us to interoperate between different languages or frameworks. Again, the whole goal of this is that you take this definition, and it doesn't matter whether you use Python or Haskell to call it or to expose the server, you will always be able to consume it from other languages. So now getting to what Mu does, what we allow you to do is to import this definition. So this is this hello service.proto file, and all this information is actually sort of imported into your file directly. So there is a bunch of things which are generated by doing this, and if I have time at the end, I'll show you a sneak peek of how this looks. But the important thing is that you don't even have to see all this code. For you can just assume that this is how you define your services, and Mu is able to use it in that way. By the way, if you've been using Haskell, you know about all these language extensions. I really don't want to show you how many language extensions you need to enable for this. But yeah, at the end of the day, there's like 10, 20 extensions you need to enable for this to work. It's something which is not so nice about the library, but we try to get as much power from all this extensions we ask you to enable. Once you have this, you also need to define the way you are going to represent your messages in Haskell. So as you can see here, I'm really following the request and reply before. You don't have to do this, but in this case, just for ease of explanation, I'm just following the same thing. They are both types with one field, and you will see that that apart from defining this, you have to include this to schema and from schema, and this is actually key of how Mu-Haskell works. This allows the generics mechanism from GHC, which is essentially something which is able to write code for you, a lot of boilerplate code, to derive the serialization to an intermediate format that we use internally in the library, and this format is then can be then easily translated to protocol buffers, Abro, GraphQL, whatever serialization format you need. So that's something nice, something we are really taking advantage of from GHC, the fact that we have this automatic derivation, which is I've always thought is one of the most powerful things that are given to us by using GHC and Haskell. But anyway, you might be wondering, why having these two steps? After all, you are importing, it is this gRPC call, which does some template Haskell magic. You are importing all this information. Why do you need to define your types manually too, if it's there on the file? So the answer is that, well, first of all, actually you don't need to do this. I'll show you later how you can not do this, but we still prefer that you define this type manually, and we try to make it as hassle-free as possible by deriving this serialization directly from you. But the reason is that we really want to see the service definition file as the source of truth, and this might not be under your control. So you want the Haskell types to remain in your control. You want to always talk about your Haskell types, but somebody else in the system might think, we need to add this extra field here, and if we just get the service definition from there, suddenly you might get a lot of errors because your types don't match what you want, Instead, what we say is, introduce this intermediate thing, and if the schema, if your service evolves over time, you can override this default serialization to introduce something to make things backwards or forwards compatible. So imagine, for example, that your uh, that your service suddenly requires you a new field to be present, and you are still working with the old version. So you won't get an error in your domain logic, which will still talk about your Haskell types. You will get an error by at the serialization when the compiler is looking at the serialization, so at compile time, but it will say, I cannot derive serialization directly from you because there is a field which is missing here. And at that point, you can decide what to do. You can say, look, I want to change my domain logic because this is actually something important, or I just want to overwrite the default serialization and say, look, I want to just say that this integer number is always 0 here. So this is the point where there might be some friction, and we have decided as part of the design to make this this deployment as serialization code and not into your domain logic code. And by the way, this thing about evolving schemas is getting more and more attention. If you look at systems like Kafka, there is actually something called the schema registry to look at this, and they have some ideas and notion of when something can be directly turned into a previous or a new version. So this is, I think this is something which is going to be more and more important over time as people realize that it's not only their data which changes over time, but also how they represent their data, something which can evolve over time. Good. After that, you just have to implement your service. So in this case, say hello takes a request message and should return a hello reply message. So in this case, what we do is we take the name, this nm variable, and then we concatenate hello in front of it. So we get the string hello and the name, and then we wrap it into this hello reply message, and we return it. I'll talk a bit about MonitorServer later, but just to finish the whole example, once you have this, you just put all these methods together. So imagine that you may not have one method in your service, you might have 20 methods. So you just put them together into a server T by using this single service function, and then you just enumerate all your methods, and finally you run it. You say run this as gRPC application, import 8080, and you just get something which replies to this message. So you see, there is some work to be done at the beginning, but at the end of the day, the implementation of the method, which is the part you're going to devote the most time to, is just a function which takes the argument you describe and has to reply something of the type of the result. So nothing too fancy, just reusing these functions we love from Haskell. So just to make it a bit more clear, you will see that we are actually using the MonitorServer there. MonitorServer is just our own Monad class, but it's just something which allows for two things. Maybe the most important is that it allows you to end with an error instead of successfully. So imagine that, well, this is not say hello, but, or maybe here, even say hello doesn't allow to have an empty string. So in that time, in that moment, you don't really want to return something. You want to return a gRPC invalid message. So this is something you can do by using this MonitorServer. You just call server error, and then you mention what is the error you want. And also, and this is in part done after the design of Servant, which is another Haskell library, but in this case to do REST services instead of RPC services. every time you are in MonitorServer, we also allow you to run arbitrary IO commands. And this is because in practice, many of these things are going to end up, talking to a database, talking to a message queue. So it doesn't really make sense not to allow IO when this is something which is so much used in practice here. Good. But by the way, you are not tied to our own MonitorServer. MonitorServer is actually a type class, so you can bring your own login database library, and this might add extra monadic layer to your monadic stack. So we allow you to do this. If you're interested in how we do this, we have some description about how we do this in the documentation. But essentially, sometimes you want to log things, and then you got an extra monad logger constraint in say hello. But then when you do the run gRCP app, you need to provide something extra which says, okay, how do I run this extra effect in the monadic stack? Good. So as I said before, we prefer that you create Haskell type, but we do not force you to. And to not force you to do, we actually bring some magic from the latest versions of GHC, and we allow you to use, we automatically derive some optics for you. In case you haven't heard about optics or lenses, this is a way in which we can model getters and setters in Haskell, so something like field access. So in this case, for example, if you compare this say hello to the previous thing, before we were accessing the name field by position because it was in this hello request, but now we are using this hash name. It's a bit bad that I cannot really, I don't know if you can see my highlighted, but this is the important part. You see this hash name, and this is an optic which is automatically generated, and it's going to work as a getter or as a setter. And then the optics library, which is just like the lens library, which was slightly easier API, defines this caret dot operation, which is about getting. So what we are saying here is that take the request, obtain the name field, and then with all of this build a record. And this record is actually be of type hello reply because this is on the type. So this optics interface allows you to write fast and furious code without having to define your types, but has a big con, which is that then you are really tied to the schema that was defined in your proto file. So if the schema changes, there is no way to introduce custom deserialization behavior because this has to be done through this from and to schema type class. By the way, I mentioned this is all a lot of magic, and this is actually even more magical, or at least I find this quite nice, because it seems that this thing is derived from the proto file, which is brought by some template Haskell magic, and this seems like you are using just hash and the name. And how are we? Do we even check that this is correct? And this is something we actually do. By bringing all this information, we can be sure that the name field is actually present, and we can know what is the type. So here, for example, we know that the name field in the request is actually a string because we can concatenate with another string. So all of this seems like a bit more like dynamically typed, but all of this is actually heavily, strongly typed. So this is all checked at compile time. Apart from normal methods, something which gRPC also allows is to have a streaming method. So you can have a streaming input and a streaming output. So you can actually choose whether you can, for example, model something like a subscription, where you say one subscription for this order, and this order is just a single argument, and then you get a stream of events, of changes in this order, or you can get a stream of input, which is like every position that you've taken, and then you just return something like a summary, so just a single value. In this case, I'm actually modeling something like there is a stream of requests of people to greet, and then you get a stream of greetings. So this is sort of a bit more complicated, but by the end of the day, you still just need to write a function to model these things. So if you've been following the Haskell ecosystem, you might know about conduits. And conduit is just one of the many different libraries to model streaming in the Haskell ecosystem. So this is what we are using in Mu, just because I happen to know more about it. So there is no real thing about using conduit or pipes or streaming or any of the other libraries. Just, conduit seems to be quite useful, and we know how to use it, so that's what we are using. So here what we are doing, and this might be a bit complicated the first time you look at it, but essentially what you have to think is that in conduit, this dot pipe is the way you pipe streams. So what we are saying is, take the source, and the source is a conduit of hello request messages. So it's a conduit which outputs messages. So it's something which a source of request messages. Then apply this function. So this map is just like the usual map for list. So for each request message, apply this say hello function, and then just put all of this into the sink. And this sink is where we expect you to put all the reply messages. So this is a conduit which takes as input messages and then just returns void. So it returns nothing because it will just consume the messages. So this whole thing is saying, take the source, take every single request message, apply say hello to each of them, and then, dump it into the sink. So send one message per. So essentially what we are doing is once we are sending one message per request. But you can do any kind of magic here. You can do, instead of map, like something more like a fold or accumulate information, or just write to a database, whatever you want. So yeah, the nice thing of using conduit is that there is a wide ecosystem around. So you can imagine something like return all the people as a stream, and you can just use this select source function, which is coming from a persistent library, which is a database library from the Haskell world, and then just pipe it directly to the sink where we expect to do things. And there is some typing involved, which requires you to write this lift server conduit function. But conceptually, or what we are doing is taking the things from the database and directly piping it into the sink. So, using this, being into this conduit ecosystem really give us the kind of tools you usually use to build this kind of microservices. Good. And by the way, I've been talking about Mu as a server. You can also use Mu as a client to talk to gRPC things. So if you want to consume this microservice we've been developing here, you can just set up a connection to wherever you are. So like localhost and this port, you call this a tab gRPC client function, which just initialize the whole connection and ensures that the server is there and alive. And then you can just start calling things. And you can see that here we are using, again, optics magic. So in this case, what we are doing is we are sort of reworking the getter as a way to access, as a way to access each of the methods there. So again, this thing here is derived from the schema I showed you before, from this import, schema import. So you have the client, you access the method, and this will give you back a function which requires exactly one argument, which is this request, which just is a name. and then it will give you back the reply. So yeah, as I said, again, we are leveraging all this optics library and this special thing in GC called overloaded labels to expose the client into a nice thing. So there is actually a lot of things you can derive if you have information about the schema. I'll talk about it at the end of the talk, because I think this is the key point of making this thing useful and type-safe have the same way. So enough for gRPC. There is also GraphQL as the other big protocol we featured in Mu. So, GraphQL authors explain what GraphQL is as it's a query language for APIs, and you all have some kind of schemas like we had in gRPC. And something you see in GraphQL schemas is that there is no such a thing as data and methods. Instead, what they have is that everything is like a record type, but can take arguments. So in this case, for example, what I'm defining is that my queries are, I can either ask for the authors, which is a list of authors, and this bang thing means that it's not optional. So instead of having to use maybe to declare when something is optional, everything in GraphQL is optional unless you write a bang. So you will see a lot of bangs in my schemas because I don't like to make things optional. And well, as I was saying, apart from the authors, you also have another field, which is a bit like a query queue, which is give me the book which matches this regular expression. And this will give you back a book. As you can see, when you look at the author has a name and a list of books. But the book has a string and also a reference to the author. So this all looks kind of very recursive. How are you able to write this thing? So if you have like a one-time query mindset, you can think, okay, I'm getting the book contains the authors contain the books, which in particular will contain the book I just query for. So it will contain a list of books. Each of them will contain its author, which again will contain a list of books, and it seems to be infinitely recursive. So how do we solve this problem? Well, the thing is, when you submit a GraphQL query, you submit both sort of the query, like here. So give me the type, some book with the title, which includes the words monads. But you also have to declare which fields of the object you want to request. So in this case, you want to get the title of the book, and then from the author, you only want the name. And if you want to get, for example, all the other books of the author, you can include author and then inside the books and then the title. But you stop there. You stop at the title. You see, this solves the problem of infinite recursion. There is no way in which you will end up in this kind of infinite loop. Well, you can do some GraphQL magic and try to get servers to try to do this. But in theory, all of it's done in such a way in which you always declare exactly what information you want and when to stop. So by the way, this is actually the kind of queries you submit to a GraphQL server. And this is the kind of queries you want to be able to consume, and the kind of queries you want to be able to give you information back. So this I'll talk about this larger GraphQL schema later, but the GraphQL schema, which corresponds to the gRPC service we defined earlier, actually looks like this. So you have a string, and then you return a string. And I think I'm actually missing the bands because this is not supposed to be optional. So, but it's this GraphQL things always have this kind of ambivalent thing. Sometimes you can think of them as methods, but they are also a bit like fields with arguments. So this is kind of a bit strange at first. And the GraphQL authors always talk about fields. So you have to always have in mind that fields can have arguments in GraphQL. But well, okay. So imagine you, instead of defining it with gRPC, you have defined just the query as before using GraphQL schema definition language. You can just import it as before, and this is something which I think quite nice from the library we've built from you, is that we give you all these ways to import information about your services directly from this schema definition file, which already exists in the wild. So just import and say, import the hello.graphql file, and this will generate two types. One is my schema, and one is the definition of my service. So importing is as easy as before. And actually, the same server is just a server for this GraphQL thing. So you can just reuse the same exact line to build a server. Actually, if you look carefully, the server T has no mention about whether this is a gRPC or a GraphQL server. It only knows about the service you are defining. And this is some information so this is about the API, about the interface you are exposing, not about the serialization format you're using. If you want to get your GraphQL server running, what you have to do is to ask Mu to expose this server as GraphQL. So you just, instead of, if you remember before, we had run gRPC query. Now we have run GraphQL app, and you again show you mention which is the port, the server, and something you need to do extra when you do GraphQL is to say which of all of these types in your schema is the starting point, the initial endpoint. So the place where you start digging for this field. So when you have this query there, you have to explicitly say that this should tie to the query type over here. So this is why you need this extra parameter when you do GraphQL. And actually, why not both? If you have the server, you can just spawn two servers talking different protocols, but your implementation is actually the same. So here I'm using this concurrently function from the async library. So essentially, this is spawning two threads, and one thread is running the server as gRPC import 8080. The other one is running the server as GraphQL import 5053. But the cool thing is, because the server is agnostic about it, it only knows about the external interface and the function you need to do, you can expose it twice without having to rewrite anything or having to tie to different frameworks. Of course, this is really cool, but this only works for the common subset if you want to do this kind of thing. So, if you have a gRPC server, this only have to match with a single GraphQL query, and GraphQL may have, has this way to say which information you want from each object, and this is something that you cannot do in gRPC because you risk entering into infinite loops. So this is not exposed. And also gRPC has streams, and I'm not showing it here, but it can be sometimes exposed as GraphQL subscription, which is a feature of GraphQL where you do not return one thing, but actually a stream of things. So exactly when this can be done is kind of fuzzy. It actually boils down to compiler says yes in this case. So there's a way in which we say this kind of things, we know how to turn one into the other. Actually, not one into the other. We know how to turn this thing into either a gRPC stream or a GraphQL subscription. And if in the common subsets, you can expose it as both. So by the way, if you want to see how a more complicated resolver looks like, so a resolver is like the term using GraphQL for the function which look at each of the fields in an object. So if you want to look about how the server looks for for a bigger GraphQL thing, it actually looks quite similar, except that now you have 2 layers. So before you only had single service with a list of methods, and now you have resolver, which has, and you have to define how each object is resolved, and to do this by defining how each field is resolved, and each field is just a simple function, and they are just, simple functions which just give you the kind of things. So find book by title, for example, I was talking before, having a regular expression and returning a bunch of books, just takes a text, which is your regular expression, and returns a bunch of books. So actually a list of book IDs. And if you look, for example, about a book title, this is something which takes the thing representing the book and returns you the text. So this is actually, again, trying to, the main logic part, try to really reuse as much simple function as we can. Of course, you might have noticed that you don't actually return like a book. When you find the book, you actually return something which is a book ID, and then the book title takes this book ID. And the thing is, this is what we call a connecting type. So it connects each object which it fields. So what is happening is that finding books won't give you back the entire information about the books. It will only give you back like the ID. And then with this ID, you can query the next things. And why we want to do this is because this allows me to request exactly the information needed. So if you are only requesting the title from the book, you only need to call book title, which takes the book ID and returns a text. Of course, there is a downside to it, which is that you cannot really optimize your queries. So you cannot say, oh, look, they are asking for the title and author of my book. Maybe I should generate an SQL query which just brings this directly. In this case, you really end up having to query several times the database, which is, of course, not optimal. We are working on it. We are actually hoping to copy some of the things from the Elixir version of from the Elixir framework for GraphQL, which is called Absinthe, which has a very cool ways to create these optimized queries. So, but for now, we are sort of using this connecting type as the way to be able to request exactly the information we need. Good. So it's been 30 minutes of showing you how cool Mu is and the kind of things that you can do with it. But I think that something which is also quite interesting is to look a bit about the internals. And the internals is actually what happens when you do this gRPC call. So what happens in the compiler when you ask it to bring all the information from the hello service.proto file and generate a hello schema type for it. So what it does is actually go into the hello service, parse it, and then generate this huge set of types. So it actually generates 3 types, so 3 type synonyms in this case, and this has all the information from the file, but in a way which is amenable for the compiler. And for this, we're using this thing from GHC 8 onward, which is called data kind. So we are representing this information as, like a big piece of data. So this hello service, if you remember, had one method which had one argument, which is a single argument, not a streaming argument, of type hello request, and then returns a single value, which is of type hello response. And this is the information from the file. And where do these hello request and hello response come from? They come from this schema, which is how we call the information about the data. So the hello schema has one record with one field, and then another record with another field, which is a primitive. And actually, if you do gRPC protocol buffer serialization, you need to annotate these things with additional information. You need to give one numeric identifier to each field apart from the textual name, and we do this as jet. another type. So we say that the field hello name in hello request has the ID 1 in protocol buffer. So this is how this all is done. So this line is just something. This gRPC line on top on the purple background is doing template Haskell, and this template Haskell is a way to run, code to run something during compile time. So it brings this information and turns it into this set of files. And because I think I'll get the question otherwise, yes, this is costly. This takes some compile time cycles. But if you are careful enough and you put this gRPC line into a single file and you ensure that this file is only recompiled once when the service.proto file is changed or the first time you compile your thing, this doesn't actually impact your compile time so much, or this we haven't found it to impact the compile times as much. So this is just a bigger explanation of what I had before. So, hello schema is, mentions that you have these two records. You have more things because different differentialization formats define records, and some others define enumerations, and others define unions, and all of those are supported by this schema language. And actually, if you look, this is the information from which we can derive our optics. So how did we know when we had this hash name that this is correct? Well, because we knew that we had a hello request. And during compile time, we could look at this type and say, hey, there is a field which has the type, which has the name. So this is correct. And furthermore, the type of this field is of primitive type text. So we know that the optic should give you back a text or should work as a getter for this text. So this piece of information is enough to derive a lot of things at compile time. So that's something which I find quite cool. And if you want to know how we do this, well, you can look at the code. But actually, it's actually using a lot of type classes. So there is a lot of type classes, like type class for deriving an optic, and this thing matches on a schema, and then it says, find the record description of the actual type we have here. So it look, if you have like a hello response, it will iterate and look up the thing until it finds the actual type it needs, and then it will again iterate over all the fields and so on. So there is a lot of type class machinery doing this, but at the end of the day, even though it looks very fancy when you look at the code, it's just going around doing recursion over these big types we have at compile time. And well, the other part, as I mentioned, is this intermediate representation we call a term, and from this term we can derive the optics or the adapters, which is how we call those realization formats. And but you don't have to write this code, so you don't have to say how to turn your hello request message into a term or the other way around. And how we do this is introducing my incredible drawing abilities. So we have this Haskell type, and there is something called GHC generics exposed by GHC. We turn this into a set of basic blocks. So you say something like, well, your type is actually a choice, and you do this with plus. So it's a choice between two constructors, and then it has 3 fields, and how you encode the list of fields is by using this star symbol. So if you have heard about sums and products, that's where the plus and times here comes from this name of sums of products. And then directly from this intermediate representation, we can derive your serialization thing. So there is a bunch of different representations during compile time. You have your Haskell type, you have your terms, you have your generics things, and this is at compile time we play with them so you can derive things directly. So this is something which I think it's using what we can get from GHC, all these cool new extensions, and actually try to put them into work to try to write the boilerplate we don't want to write. Well, I mean, I had to write it because somebody has to write it, but for everybody using the Mu library, this is something which happens under the hood. So that was all. Let me finish by a word from our sponsor, but I mean the sponsor for the development of Mu, which is the company I work in for 47 Degrees, which I'm very thankful for because it allows not only me, but also my colleagues to contribute to this project and also to other projects in the ecosystem. And I just wanted to mention, that's my advertisement line, that we'll be offering public trainings quite soon. So stay tuned if you want to learn a bit more about fundamental and advanced course about both Haskell but also other languages. We always try to follow this approach of functional first. So we try to teach you how to do things in a functional way, in a pure way, trying to keep your side effects under control. So if you are interested in this, just contact me or contact 47 Degrees directly. But as a summary, I've been talking about the Haskell version of Mu. It's a library to work with microservices. It's there. The docs are there. If you click on the small links, say next, you will actually see more about the new things I've talked about. Currently, both gRPC and GraphQL are supported. But the other takeaway from the talk is that a lot of information can be represented in the type level in the current GHC incarnation. And we can actually import this from other sources if we play our template Haskell well. And this is extremely powerful because it ensures that at every point, the application, the things we are building, agree with the contract. And this contract doesn't have to, as I said, it doesn't have to be in Haskell. It may come from an external source. So yeah, thanks for listening. And I'm happy to hear questions from all of you.
Yeah, so thank you very much, Alejandro. So I guess for the next couple of minutes, we can take questions. I think I can go first. The first question that I have is there any like a sample project somewhere online where people can like see Mu-Haskell in action? So
Yeah.
if you want to like get started.
So if you go at the URL I showed at the end, so the official place, and you look at the code, we actually have like 5 different examples ranging from a simple thing, something which shows a streaming, something which tells you how you can connect to a persistent database or how you can introduce logins. So we have a bunch of examples already worked out about it.
Cool. I think Dimitri raised his hand. So Dimitri, you can go ahead and ask your question.
Yes, first of all, thank you, Alejandro, for your talk. It was really interesting and informative. And I have a question. You use a lot of type level stuff in Haskell, and I wonder what was the most challenging part in implementing? Was it like generating getters, or was it serialization type classes? Which part of this project was the most difficult?
So actually, well, first of all, being able to import this kind of proto file into types was kind of hard the first time we did it because it involved a lot of different levels. So you are reading a file, so you have to parse it, and this comes into some kind of algebraic data type describing your thing. And from this, at compile time, you have to generate types. So this was all kind of too many levels working at the same time. So this was hard. And the second part, which was hard, is actually figuring out how we encode this information. So because how we encode this information is exactly what we can express. We started, like we want to do gRPC with protocol buffers, and then suddenly we want to introduce another format, and this was not good enough. So we have to refine this thing. So I think it took us like 3 versions to come to a good way to encode this kind of thing. So yeah, I have to say that this type level information can be very powerful, but it's so pervasive in your code base that if you suddenly realize that you made a wrong decision, and we realized this several times, you can see huge commits just saying, make everything compile again, because then suddenly breaks. So I would say this is quite challenging.
Okay, thank you very much.
Yeah, thank you, Alejandro. We have some questions from the folks watching from YouTube. So I think I will just ask on their behalf. And then after we go through the questions on YouTube, perhaps if some other people here also have questions, they can ask. So the first question is from Hernan Rashert. He wrote, Alejandro, is it possible to share an implementation between Mu and Servant?
So right now, it's not possible to do this, and we are looking about how we can do this. But the main problem we found is that we haven't found an easy way to map the notion of routes in a REST service to what we have now. So what we have now, it's kind of the method has a name and that's all, and takes arguments. But if you have like a REST route, then you have to encode not only sort of the name, but also this argument is going to be placed here, and this argument is going to come in JSON format into the body. And this is something which the servant does very well, but we haven't found the way, to be able to do this while not destroying the interface for gRPC and GraphQL.
Thank you. I'm trying to get my YouTube to load again because I had to refresh the browser so I can see the other question. But maybe in the meantime, while it's loading, if someone else is in the call, if you have a question.
Somebody has raised the hand. Jury.
Okay.
Yeah. Hi. Thanks for an awesome talk, and I would like to ask this. You said that our schema specification might evolve over time, and we generally don't have control over it. Is there any kind of registry in Mu itself so we can keep track of those versions?
No. So no. Short answer is no. We are trying to figure out how we can connect to Kafka registry, so a Confluence registry. I always forget what is the right name, but it's essentially a registry for schemas where you can put these things. So we would like to be able, so somehow that you can say now download the latest version of the schema for this. But Mu itself doesn't keep a registry. So it just assumes that you somehow get this schema from somewhere, and then it starts from there and then works from there.
Oh, okay. Thank you.
Cool. I have the questions loaded now. So Armando wants to know, will the servant monad need to implement the monad server instance?
Sorry, once again.
Armando asks, will the servant monad need to implement the monad server instance?
No, so the server, so there was several things on there. So server T is not tied, so it has the same name. It has monad server and server T, but they are actually not connected. So monad server is what you use to implement each of the methods, and then you put together a bunch of these methods, and then from this you build what we call a server T. And but no, if you don't want to do anything, you can just use monad server there, and there is a default implementation which is called server errors and IO. So it's just the bare minimum to do this if you don't want to bring anything else. So yeah.
Okay, Cool. We have two more questions from YouTube, so I'll just quickly ask the first one. Rick Vanta wants to know what happens if you provide a non-existing key string to a schema definition. For example, what if I were to make a typo in hello request in the schema type definition? Will the compiler tell you there's been a mistake, or will it generate incorrect code?
So that depends on the kind of mistake you've done. So, for example, if what happens is that you have written a wrong name there, and this is mentioned from another type, then what will happen is that it will say, you are mentioning this type here, and I cannot find it. Of course, if, for example, you have an enumeration and it's not used anywhere else, well, there is nothing we can say. So most of the things we check, some of the things are not actually found at compile time. What happens is that when you try to derive the serialization, so when you do this to and from a schema, then it suddenly realizes that there is a missing thing. So if you do this two-step thing, you will find it into when you define your schema. But yeah, so I think sort of the answer could be that sometimes we generate type information which is wrong, in the sense that if your schema is wrong, we are generating just a copy of your schema. So we just generate wrong schema. And some of these we can detect when we import the schema. Some of them we can detect only when we try to derive the serialization, because there is something missing. Some of them we can only detect, for example, when you are deriving an optic because you thought the name was name and it's first name, or things like this. So depending on which things, there is some things are detected at different moments in time.
Cool. There's another question. This about the error messages. So Luke wants to know, what are the error messages like? Has there been made use of custom type errors? Maybe since there's so much type level information.
Yeah, so we've put quite some effort in trying to give good error messages. So for example, if you use these optics things I was mentioning, and then you say a field which is not present, the error you get is actually this field is not present in the type. Having said so, there is something we are still working on, trying to figure out how to solve, is that sometimes the inference of the types is not good enough. So sometimes what you get is not your error is not actually you are doing something wrong. You get one of this ambiguity thing where the compiler essentially says, I don't know what you're talking about right now. And then you have to provide extra information. So like, for example, in the example I was showing about the with the optics, the fact that you could use the name of the field relies on the fact that this was annotated, that this is coming from the hello request type from the schema. If you leave this out, your code won't no longer compile, because it will say, I don't know what type you are referring to. And if there is no type to refer to, you cannot even start looking inside the list of fields to see whether this name field is there or not. And this ambiguity thing is actually what seems to be a pain in the ass most of the times. And I don't know any technique to help with this right now. I would really like that this was the case. Believe me, I've devoted 4 years of my life to try to figure out how this can be done, and I don't know the answer. So
Thank you very much. While you were talking, another question came in. So I think we just quickly take this, and this will be the last one from YouTube. So Hernan wants to know, he says, I need to encode an Havro scheme to use with the Kafka bindings for Haskell. That's the HW Kafka client. So is it possible to use the Avro definition code outside of Mu?
Yeah, so I mean, if you have this Avro definition file, you can use it to derive a client or derive a server using Mu, but you are also free to use any of the other possibilities into the Haskell ecosystem. So the whole point of this Avro definition file is that regardless of the framework you use, you can actually use it. But actually, I mean, I have even better news because we are working on a Kafka client using Mu. So this is not something we have finished yet. But if you look in the repo, there is like a Mu Kafka bindings, which actually use this HW Kafka client, and then uses the Mu layer on top to do this serialization automatically. So. But yeah, in theory, it should be possible to use the same Avro definition which you use in Mu in any other framework or language you want.
Cool. Thank you very much. If there are no questions from the people in the call, I guess that will be it.